Okay, in this video here, we're going to be looking at question 9 from homework 3, and I'm going to walk through how I would solve it. Hopefully it seems pretty simple when it's phrased this way, and hopefully you can understand why I code things out the way I do, mainly for simplicity. So the question here, and I found a little issue in the problem statement. These said 15 years. I would suggest you do it for 25 years since it's over the next 25 years. But I think you could have figured that out. If not, oof, now you're watching the video. So your manager believes that a new furnace would be cheaper when considering how much it costs to run the old furnace if we buy it and run that for the next 25 years instead of this old furnace. The new furnace is $7,000. It uses 15 kilowatt hours per run. If you remember, the old furnace uses about 34 kilowatt hours per run. And the cost of energy right now is 25 cents per kilowatt hour. So, we want to know, should I buy the old one or should I buy the new one? You can be however clever you want in solving this question. What I'm going to do is I'm going to follow these steps. Step 1, I'm going to determine how many kilowatt hours the new furnace will use over the next 25 years. Well, let's go ahead and do this. So, let's just say usage. We'll say new furnace. Usage, 25 years. It's going to be equal to 15 kilowatt hours per run times 365 runs per year times 25 years. We're going to go ahead and note this down. Kilowatt hour per run times runs times years. And that should go ahead and get us the right answer of kilowatt hour years. Kilowatt hours total over 25 years. And then we're going to say, okay, so what is that value first? What's our benchmark? What are we working against? This new furnace is going to be about 1,300 kilowatt hours. Nice. So that's step 1. So for step 2, what's the old furnace going to run at? Well, we can go ahead and look at the answers from, or the results from problem Q8, and we'll see this little slope here. What this represented was the change in performance from 1990 to 2018. So if we go for the next 25 years, we're going to go from 2019 to 2039 or whatever. And so we can imagine either this trend projects outwards or maybe it slopes and does sort of like a square root behavior. I'm going to assume linear. You assume what you want. It's part of your expertise here. So, if it's a linear trend, we can figure out the slope. Well, the slope is going to be equal to rise over run. Well, what's my rise? I actually sort of have the answer to this. Q8 has the answer to it. The rise would be, well, what were the values in 2018 minus what were the values in 1990? Because that's my rise. And then my run, well, that's going to be, well, the actual years it happened over. So I can get my slope like that. So this is how much increase we have on average kilowatt hours per run each year. And then we need the bias, or the b part. So y equals mx plus b, since we're modeling this line here. Well, I can rearrange this equation to get b equals y minus mx. Well, what is y? Let's take one of these points. Let's say it's 2019. And we have the value for m, and the year is 2018. So now we can get our bias here. And we can see it was negative 239. And this is why you don't extrapolate, because that number doesn't make any sense. It takes negative kilowatt hours per year if you're running this in year 0. Okay, well, the next thing I'm going to do is I'm going to wrap this up in a nice pretty equation where I just need to give it the year. So we'll call this kilowatt hour per run, and you give it the year, and what you get back is kilowatt hour per run, where you have m times x, which is the year, plus your bias, and we'll return that value. So now as a sanity check, what I'm going to do, after I define all of this, I'm going to check this at 2018 and see if it matches the actual answer at 2018. I'll do the same thing for 2019 and see if that matches. Then let's just go up to like 2020. Sorry, 1990. Let's go up to 2020. So it's just a little bit bigger than 2018. Perfect. So that's the behavior we expect. That function is going to work well for us. Now what do we do from here? Well, we have a future projection of what this old furnace is going to do. Let's go ahead and just loop through this. The old kilowatt hour total is going to be the sum of each year's total usage. So it's going to start at 0, since we're going to say how much from year 2018 to 2039 or whatever, or 2019 to 2039, the next 25 years. I think that's the math. So we're going to say how much does each year contribute? What's the total value for each year? So for year in range, we'll start at 2019. We already have 2018's data to 2019 plus 25. I keep doubting myself when I say this. Let's go ahead and okay, wow, 25. So it's 2044. Great. So for year in this range from 2019 to 2043, since we don't include the endpoint, what we're going to do is we're going to get the average kilowatt hours per run for that year. So we're going to grab average kilowatt hour per run for that year, which is kilowatt hour per run at year whatever we're on. And we're going to go ahead and multiply that by 365, because we have 365 days in a year. And that'll give us the kilowatt hours in a year, or in that year specifically, since each year has slightly different kilowatt hours per run on average. And then finally, we can take the old total we had, so all of how much contribution we had from all of the previous years, and we'll add, so this is all the contribution from all the previous years, we'll add the current year we're on, and we'll update so that the next year we have all of its previous years. Let's go ahead and run this, and we see we get 300,000. Now as a sanity check here, there's one thing, and I suppose we could have done it first, that we can do. We can say, well, let's pretend it flatlined at 2019, and that's where it stayed, or at 2018. Well, what's 2018's value times 25? So over 25 years, run every day, 365 days. Okay, so that's 300,000 already. Great. So it looks like our value, our projected furnace usage, seems like it's in a reasonable ballpark. Now the final part is to simply compare those. So we have new furnace usage over 25 years. We have, let's go ahead and call this old furnace. In fact, let me just copy paste. Call this old furnace usage over the last 25 years, and that's equal to the old kilowatt total. And let's see how much money we save when we use this many kilowatt hours. Okay, so we have the old furnace usage. We're going to go ahead and grab the difference. So the new furnace usage minus the old furnace usage will give us the difference between the two of them, aka how many kilowatt hours we save. We'll go ahead and multiply this by 0.25, 25 cents per kilowatt hour. So dollars saved. And let's go ahead and make this its own difference in kilowatt hour. And that difference times the cost of 25 cents. That's going to give us our dollars saved. So it looks as if we absolutely should buy the new furnace. So I'm going to say, should we buy it? Yes. I hit run. And you're right, we should buy the new furnace. Because the answer says right there. Great. So hopefully you followed that. Now, that's only one way of doing it. And in fact, the easiest way of doing it isn't to do any sort of projection out into the future. It's to skip this entire thing and say, well, let's say we run the old furnace's specs against the new one, where it was simply just, what was it, Q8 my answer at 2019. I mean, this is honestly the easiest way of doing it. But there's lots of ways you could have approached this problem. So it's 34 per run. There's 365 runs. There's 25 years. That difference, even if the furnace doesn't get any worse, we still save a lot of money by buying the new furnace. So, in fact, we can say dollars saved is greater than dollars spent. If I write there, I'll say print. Let's get fancy here. Should we buy the new furnace? And voila, true. Well, good luck. Hopefully that helps explain the problem a little bit, and hopefully that clean solution lets you think about the code and, maybe the question I asked a little bit better.